Okay, so now we are dealing with solar cooling after having seen the solar heating. I would like first to introduce this. We will work on this principle this afternoon on solar cooling by what we call desiccant cooling. Solar cooling or cooling is very important thing, and it has been developed by centuries and centuries in very hot countries. And one of the more efficient phenomena associated to the cooling is evaporation. Okay, so we call that evaporative cooling. That means that if when water is evaporate, it take a part of latent heat in the surroundings that allow to decrease a bit the temperature. Okay. So here you have an illustration of outdoor air conditioning system. It's stupid to say outdoor because it's fully open, but when it is very hot outdoor, you may have seen some thing like this. It's a kind of brumisator that inject very thin droplet of water, a kind of fog that evaporate. Okay, as soon as the thin droplet are outside, they evaporate and allow to cool down the surrounding. Okay, so it's used in very hot country, in open space, in railway station, for example, or even along some paths where it is very hot to walk. You have this kind of injection of thin droplet of water that evaporate and allow to decrease the temperature. Have you also seen this kind of diagram, psychometric diagram, or not? So yesterday Dr. Pankaj gave you, I think, one. So we will work on it this afternoon to see what is the operating condition of what we call desiccant cooling. Of course, desiccant cooling is not only based on this, because you can imagine here inside, if we were injecting thin droplet of water, at the first stage we will feel comfortable. It's cooled down. But at the second stage, you will feel very uncomfortable, like in a humid tropical country. Okay, humid, hot tropical country. So that means that we are obliged to dry at one stage, to dry the air and to humidify the air. So it's more complex than this simple thing, but the main thing which is behind is evaporative cooling, behind the desiccant cooling. It has been developed, as I say, in Persia, so now Iran. It is here, you can see wind tower, okay? So wind catcher, we can say. It is a very interesting tower that don't use chimney effect as yesterday, but when the wind is crossing this tower, there is some tube where there is injection of air inside, collected, the wind is collected, and there is some tubes that are open, and the wind which is crossing is inducing a pressure loss that allow to the air to be aspirated. So there is a double operating here tubes. One are injecting, catching the wind, injecting. One is aspiring, exhausting, allow to exhaust the air. And what is here behind? It is water tank. Okay, water tank for usage, okay, of the water, but it is also used to cool the air. And they have developed very interesting underground tubes in order the cool air is distributed to the house. There is still this kind of system of evaporative cooling. You can see also in Romanian it was almost the same. There was inside the house some basin, fountain. Okay. In Egypt also you see all around the building and sometimes inside the building some basin of water. It was nice, but it was also for cooling, because the water, when evaporating, is cooling down the ambience. Okay. Here another example of this evaporative cooling in Mali. So here is a house. Here you have a kind of linen at the top. During the night, people are putting some water. Okay, so the linen is completely full of water. During the day, this is drying, so they evaporate, and the cool air is going down in the house because due to this evaporation, and so it's allowed to cool the house. Interesting. That has been also developed in a museum in the United States, where you have also wind catcher, the wind catcher, and here you have a kind of system of basin. There was evaporation and injection in the building, so it's passive, free cooling, okay, by evaporation. I like this phenomenon. So in reality, we will deal with this system. It is the traduction, the implementation of this principle in HVAC system. Okay. So how it's working? As I told you, so here you have the house, okay, or the building. You have a double flux management of air mechanically, okay. You manage the injection of fresh air in the building, and you manage the exhaust of air, okay. As I told you, if we want to humidify the air by evaporative cooling, first we have to dry it. So before the air is going inside the building, it is crossing what we call desiccant wheel. Okay, desiccant means dry. Okay, so it could be salt. If you want to have an analogy, it's a kind of salt. Okay, you see that salt with humidity, there's a good match. Okay, so the salt, it's reality more silica gel, has a good attraction with humidity. Okay, voilà, battery, and so catch the humidity of the air. Okay, and then at the outlet you have dry air. Here you have an heat exchanger, classical heat exchanger. It's allowed to be cooled by the air which is exhausted. In principle, inside the air is cooler. Okay, so the air that you will extract is cooler. The air that you will inject is hotter. So you have a heat exchanger to allow to cool a bit the air before it is going in. And then here you have the injection of humidity, so evaporative cooling. So it's here that you cool down. Okay. Why there is also a humidifier here for the air exhaust? What could it be for? Okay, so it's for air inlet, and this is for air extraction. Why we are using also here evaporative cooling? We are using here evaporative cooling in order to decrease the temperature of the air, okay, before the heat exchanger. Like this, the heat exchange is better, okay. We decrease the temperature of the exhaust air is cooler, but we decrease it again in order to increase the delta T here. So to allow to have more heat exchange. Okay. Then we are heating this air, and it is here that the solar thermal is coming. Okay. We are heating this air just before crossing the desiccant wheel. Why? Because we want to dry the desiccant wheel, okay? Because the humidity is collected here, we have to get rid of. If we don't get rid of this humidity, at the certain stage, the wheel will be fully saturated. And if the wheel is fully saturated in humidity, the process can't operate anymore, okay? So we are heating the air before crossing the desiccant wheel in order to evacuate the humidity, okay? And to be sure that here we can catch humidity again. So it's something that is running very slowly. It is a wheel which is running slowly in order to catch humidity and to get rid of humidity. So it is the principle of desiccant cooling. So solar thermal cooling by desiccation. Okay? So you can say that finally the solar thermal is not used for the building. It is evacuate. Okay? But it is necessary.
But here we can control humidity as well.
Ah yes, here. Yes, due to that, yes. And it's important to control the humidity, because if you don't control it, it could be very uncomfortable inside, or the process could break down. Okay? So it is a modern traduction of evaporative cooling that has been used since centuries. But because we are in a closed building, in the past there was no windows, it was fully open. Okay, so no problem to inject, to have a swimming pool in your house, because there was no windows, it was open. Okay, so if there is evaporation, at a certain stage humidity is going out. But here we are closed. So if we inject humidity, it will become too humid and uncomfortable. Okay? So it is the main principle that we will study this afternoon. Okay? And what will be our target this afternoon regarding that? Compared to classical cooling system, what will be our objective? It will be to see if we are less consuming electricity than a classical heat pump, which is very efficient in terms of consumption. Heat pump efficiency could be 300%. Okay, so it's very efficient. Should we do, with thanks to this system, is the electricity power is lower or not? And the other point, what amount of water we are consuming? Okay, if I want to cool down this amphitheater, do I need a full truck for half a day, a full truck of water, or should I need a small tank of water? Okay, it's very important. Obviously, we will see that it is very efficient in terms of electricity. But you have seen the complexity of the system. It is very delicate to control. Okay, to manage. We have to be sure that all the humidity that is taken here is fully extracted. Is not partially extracted, is fully. Because if it's only partially, after a couple of hours, it will saturate. Okay? So the humidity that is collected here has to be fully extracted. If it's not the case, the system will break down after several hours of operating. Question? Oh, I like a lot this system, but it's very complex. Finally, the physical phenomena that are behind are very simple, but after to put in practice and to control this system, it's very delicate. Okay.
I have a few queries and then scope of doing some kind of combined research. Here in this part of the country, during the summer, we reach a temperature of about 38, 39 degree. But humidity is close to 90%. So it is very, very uncomfortable. Every time you will sweat. So those who can afford, they can buy commercial air conditioning systems, which is operated by a vapor compression refrigeration system, and which uses refrigerant. Now, can we devise a mechanism which is lower in cost, so that the people who is living in the countryside, they can also afford with this kind of system? So what we need to really do is to reduce the temperature, reduce the humidity. Temperature is fine, it's 35, 34, 30 or maybe 38. That is okay if we could reduce the humidity.
Yes, so, it could be possible. It is like a classical cooling system. In some country where it is not so hot but very humid, it is used mainly to dehumidify. We will see that this afternoon, that it is the equivalent. Of course, all this loop is the equivalent of a classical cooling system. Of course, if it is not equivalent, it's not good. So we will see this afternoon what a classical system is doing and what are all the transformations to do the same thing as a classical system. But it is right, when it is too humid and not so hot, it is used to dehumidify more than really cooling. The more important is to dehumidify. Yeah.
But at the same time, that has to be economic. That we need to check.
Yes. Economically, it's more expensive than a classical. It is the same parallel as PV and solar thermal than heat pump and this.
So where we are dehumidifying the air by using the solar collector or solar energy, so their material will be a major important thing, because the air is containing water and we have to dry it. So it should be like the material will be a challenge, that it should not be corrosive or it should not be deteriorate after certain time, because that will lead to a efficiency degradation of this system.
Yes, you're right. We will see this afternoon if we have time. I don't know if we progress. It will depend of our progress in the tutorial. But of course, there is at the backside a need of thermal storage in order to ensure stability when there is variation of solar energy or no solar energy.
Yes, yes.
So in the whole system, I will propose you this afternoon, if we have time, to study the system, and then we will design the solar thermal storage. Okay? It's very important. And it is the same. So for such a system, if we will take in consideration an amphitheater like this, a bit bigger, and what autonomy we have to choose? Will it be so? It's not reasonable to say 2-3 days like in PV, because there's no sense to store solar thermal for 3 days for cooling. And usually, when there is no sun, you need less to cool. Okay, so it's related to the cooling needs are fully related to the sun. So it will be at the scale of the day. Okay. Imagine this morning it is sunny, okay, and this afternoon it becomes cloudy. but it will still remain hot. Okay, so typically for such a system, the design of the solar storage, the storage will be around 3 hours to spend the afternoon in the same condition of. Okay. So we will see that. I hope we will have time to deal with also the thermal storage with phase change materials or water. Okay? Other question? Yes?
So, okay, thank you. Inlet air cooling system. No, second, yeah. When air is coming from outside,
yes,
it's here. Yeah. Then it will be cooled
at the heat exchanger.
Heat exchanger. Next, from here, cold air will come to building, and again from exit. Again, it will be cooled.
Yes.
So, the air coming from outside to the building, its density will be lighter than the air going from up above. So due to density difference, the cold air from above will go down.
Yes. Well, this is just a picture of, and it is not natural. It's not natural ventilation. It's mechanical. So when you extract it, whatever, if it is down or you extract the air, so it's mechanical.
But because of density difference, if that air comes down, it will facilitate cooling, because the air coming from above side, it will be more because.
But here in this HVAC system, there is no connection, direct connection between air here and air down. It's fully separate.
Okay.
Of course, because there is also pollutants. When you extract the air, is to have a more to improve the quality of air inside the building. Yes, because we are all injecting some pollutants. There is some pans that are injecting COV and so on and so on. So you renew the air because you want to clean the air inside. Okay, so there is never direct link between exhaust air and new air. Okay, just the link is by heat transfer here and by the desiccant wheel here, but there is no connection between two tubes. Okay. Yes, it is a double flux system that are now compulsory in new building in Europe. Okay. This system is double flux, that you are mastering the inlet, and you are mastering the outlet, because the building are fully tight and very well insulated. Okay, and it is allowed during winter time. This is heat exchanger during winter time allowed to recover a part of heat which is rejected outside. During winter, it's also operated. Of course, you erase the humidity, or you can use it if you want to inject humidity, because the air is dry when it's cold outside. But this heat exchanger is still used during winter, because the hot air which is coming from the building, which is extracted, is exchanging with the cool air which is coming in. So the double flux system plus heat exchanger is now compulsory in every new building in Europe.
Yeah, now I understand.
Because we want to master exactly the energy loss. Okay. So we'll see what it will imply on the in terms of transformation. It is very simple transformation. It is simple heating, simple cooling, or evaporative cooling. And evaporative cooling is an adiabatic transformation. Okay. So we'll see it's some series of very simple transformation. Okay, so this is an image of this installation. So you have the air inlet, the desiccant wheel. Okay. Here you can have also an heat exchanger, rotative heat exchanger, and then you see the way to humidify. There's different way. You can have a kind of sponge. What we see here, a kind of sponge with water, and the air which is crossing this sponge evaporates the water. You can have also some kind of sprinklers that injects very small droplets of water. Okay. Could be, yes. Then you have two other category of cooling system. So we have seen desiccant cooling, okay. There is two others which based on the sorption phenomena, okay. So there is absorption machine or adsorption machine. It's just to recognize what kind of media are implied. Do you know the sorption? So it's implied two media. Okay. For example, in the desiccant cooling, when you have salt and humidity, when they match together, it is what we called adsorption. Okay, adsorption, that they have a special relationship, very strong. We call that thermochemical attraction. So they mix together, and this reaction generates heat. Okay, when you have salt and humidity, when they match, it injects some heat. Okay, it's warming. At the reverse, if you want to recover your salt, you have to heat this mix. Okay, you have to heat the mix, and then the humidity will evaporate and separate from the salt. Maybe you have seen this kind of, if you leave your salt like this open in a humid atmosphere, after 2 days it's a block like this, because there is absorption with humidity, okay? And during this absorption phenomena, if you are putting some flux meter or thermocouple, you will have seen that there was injection of heat. Then when it's finished, you have a block like this, a very strong relation. If you want to separate again, you have to inject heat to warm that. And then humidity is separate. We call that desorption. Okay. So sorption machines are based like this. Two couple, two media, when they are close, they are attracted and mix together and release some heat. Then it's a very stable mix. When you want to separate again, you injected some heat. At a certain point, one of the two will evaporate and separate. Okay? So this principle is used to store energy or to generate cool. Okay? When you want to separate that, you have to inject some heat. Okay? And it is during this phenomena that you will take some heat. If you inject some heat, that means that you take some heat. Okay, so this principle, and when they mix together, you give some heat. Okay, so you are heating in one sense, cooling in the other sense. Okay, so it is the principle of sorption. When it is a solid, like the salt, plus humidity, we call that adsorption machine. Okay, the more common adsorption machine is not with salt and water, it is with zeolite. Zeolite, it is solid materials, solid porous materials, plus water. Okay. Zeolite plus water. It is adsorption machine, so it's a solid. You bring humidity, they mix together, inject heat. When you want to separate, you are heating them separate. Okay. Adsorption machine is solid plus liquid or gas. Absorption now is the same phenomena, but it is between two liquid, or one liquid and one gas. Okay. Example: the very efficient couple of absorption is ammoniac. We said ammoniac plus water. Okay. The same. When they are closer, they mix very well and generate heat. Okay. When you want to separate, you are heating and there is evaporation of water and it's separate. You have also a bromide lithium plus water. Okay. So this kind of machine is called absorption machine. Ab, you recognize it is liquid, or ad, you recognize it is solid plus liquid. Just the main difference, but the physical phenomena that are behind, we call that thermochemical reaction, are very similar. Okay? So it is well used in storage and also used in solar thermal cooling. Finally, you have all seen what are the main components of a classical cooling system, heat pump. You have four main components: evaporator, condenser, pressure loss, compressor. Okay. The objective of this machine, adsorption and absorption, is you have the same three components: evaporator, pressure loss, and condenser. And the principle of this machine is to replace the place where you are consuming electricity, so it's replace the compressor by the equivalent with this phenomena. Okay, so if I had a classical machine, cooling machine, I get rid of compressor and replace by different transformation that do the equivalent. Okay, so there is on the four classical elements that we see in a cooling system: evaporator, condenser, pressure loss, and compressor. You get rid of compressor and replace by transformation that replace this mechanical compressor by a thermochemical compressor. Okay, it's just to give you an idea of this kind of machine. So it has been developed since a long time. At the beginning, this machine were developed. The bring of heat was not solar, was made by combustion. These machines are existing since a long time. And they were using a burner that brings the heat. Okay, so you have fridge, absorption fridge, that have been developed since the 80s. Used, for example, in hot country to design chambers dedicated to the conservation of medicine, for example, where you need, to have a cool temperature, stable temperature. In a camper van, when you have a fridge that you are not connected to the grid and not PV on your roof, it was a burner. It was a small burner fridge. Okay, so the heat that is necessary to prepare was brought by burner. Due to the fact that why not bringing this heat by solar thermal, it's a good idea, but it's also has induced some issue regarding the stability. As I was telling this morning, thermodynamic machines don't like instability. They are very efficient when they operate in stable condition. Okay, so the problem with solar energy is that could fluctuate, variable, and so on and so on. So the challenge was how to maintain a stability, to have a good efficiency, a good thermodynamic efficiency. Okay, but this kind of machine was existing since a long time. With the heat was bring by a burner, and there is still. For absorption machine here, the surface of solar. So first you have to very often have vacuum tube. Okay, you need to reach at least 130, 140 degree to heat the couple in order to separate. Okay, so classical flat plate collector is not enough. You need that kind of technology. Just to give you an idea, if I want to cool down hotel of 5 floors, you have to recover the full roof of this kind of solar technology. So it's equivalent to 1/5 of the surface. Okay, I'm clear on the. So just to give you an idea, if I have a full roof, I can cool down 5 floors. So it's an important surface. That means that if you use it only for cooling, it's delicate. Because what to do when you don't cool? Okay, so usually it's well adapted for buildings that have need of cooling and big need of hot water. So hotel, because there's shower, and hospital. Okay, and more developed application in Spain, it was for this kind of building. So you need to cool, and you need hot water. Okay, because if not, what to do about all this hot water? It's delicate. So well adapted for hotel. So you see that there is some installation that installed since a long day. It's quite stable after. The price compared to PV, we come again to the price that makes that this is not so well developed now, because if you imagine that you recover the full roof of the hotel of PV, you can cool and use electricity, so the same challenge each time, but in terms of technology it's very good and interesting, because it is when you have sun that you need cool, so it's good. Okay, but it has to say that it is a big competition in terms of business with PV.
This is more sustainable.
More sustainable, and if you very well adapted if you need to cool and hot water. So for some typical building or even industrial building where they need a lot of hot water and to cool, it's very well adapted. And question, it is clear the principle which is behind. So absorption and absorption is the same. So here it is the principle. So it's absorption. We will see maybe later, but it could be used for storage also. So this principle, when you heat this kind of couple of media, so you injected heat by sun, by solar energy, you separate them and you can keep them in 2 different tanks. There is no loss. Okay, no loss, because it's not sensible heat. There could be in 2 separate tanks like this at ambient temperature. It is when you put them together again that they will release the heat that you have stored when you are injecting solar energy. Okay. So you have this option. So when you are injecting heat, you have desorption. You are separating the two body. The water vapor is in one tank and the other in the other tank. There is condensation. Then it becomes liquid. Then you can mix again and. So this is my machine, okay? So you can recognize that there is a condenser, classical in a cooling system, evaporator. I don't know the name, where you generate pressure loss, the detender or what is, you have four main elements. Expansion? Okay. So that allow to decrease the pressure, okay. So this, and usually in a classical cooling heat pump, this is compressor. Condenser, expansion room, evaporator, and then you have compressor, and it's run like this, okay? So the compressor is out, and we replace by this, okay? So where you have the injection of solar energy at the desorber level, so you are heating the two couple. One is going to the vapor is going to the condenser, so it could be water vapor. The condensation release a part of it, okay. Then you have expansion van. You are going to the evaporator. This take a part of it, like in a classical heat pump, and it is here, so that you are generating the cool. Okay. Then it is the liquid is then injected, combined with the pure solution when it was separate, and then come back to the desorber, and so on and so on. So it is the principle of this adsorption or absorption machine. So this is more absorption machine, and the solar energy is bring here. Whereas you take the heat, you cool here. Okay. So it is a reverse process. Here you have some elements. So silica gel plus water, it is also what is used for desiccant cooling. So it is solid plus vapor of water. And you have also activated carbon plus water, zeolite water, calcium chloride, zeolite plus ammoniac, okay? So different couple. Now it is an adsorption machine, so it's more delicate because in absorption machine you can make the fluid circulate as you want. You can recover. With adsorption machines, that means there's one solid and one come liquid and vapor and liquid and vapor. So you can't put the solid in one place and then displace, and so it's fixed. So it's a kind of a block like this, okay? And you have a system that in at the top we imagine a kind of tank, okay, with a porous media, okay, fully saturated in water, okay, like volcanic stone or zeolite water is the same. So fully saturated at the beginning. You bring heat at the top of this tank, okay? What will happen? In the zone where you are heating, at a certain stage, the water will become vapor, okay, and will be desorbed, okay. So this you are drying finally the porous solid media, and the vapor naturally the vapor is leaving, okay. Then you bring the vapor in the condenser, the same element as and at the condensation point, when the vapor is condensing, it generates heat. Okay. Then you have the pressure loss chamber here, so to go down in pressure, and you arrive so at the evaporator. Okay, and so the evaporator, of course, is taking some heat. You have vapor, which is going naturally. This is a picture of natural, so which is going naturally to the porous media, okay, and then saturate again this, okay. So you have the two stage, condenser, evaporator, then going then again, okay. So when they mix together, here at that stage, it's release some heat. So it's working like this. You inject solar energy here, separation of vapor, going to the condenser, generates heat, so you can use it for heating the water, for example. Going to pressure loss, then evaporation, that takes some heat, and naturally going to the absorbers. And when they mix, they melt, they meet together again, it's release some heat. It's very interesting because there is absolutely no electricity consumption. No need, okay? Whereas here, you need to have a small circulator that bring the fluid in one place to bring to another place, okay? But here, it is fully passive, automatic, without electricity consumption. That is the interest of this machine, adsorption, because all is natural. You are heating it, the vapor naturally is exhausted, okay? Go out. Come in the condenser, then you have pressure loss, evaporator due to the pressure loss, okay, that takes some heat, and as it evaporates, it's going up, okay, to the tank. So very interesting also, not so developed, unfortunately, but there is industrial product. The more efficient in this kind of machine are Japanese, okay, and there is industrial manufacturer of such a machine, and the best are Japanese. But it's very interesting because it's fully autonomous. Just need some heat from sun, and the circulation and the pass of the one of the media is natural. I like also this. Do you have any question regarding absorption, adsorption? Yes?
By giving this one input in that first diagram, we got here two outputs like heat extraction in the evaporator and the TCS. So is this possible? Just by giving one input and we got two objectives, like it may disobey the second law of thermodynamics or like. Yes.
What?
We also got heat equals here, no?
Yes?
Means we adding the heat at first, and in second round, here we at first extract the heat
Yes.
from the room. Okay, so first objective is we got, and simultaneously we also got heat here. That's why
Yes, we can then after try to to enhance this heat which is released, for example, for heating some water. Generally, you try to recover a part of this heat which is lost. So for heating for domestic hot water, for example. But it's just to show you two different pictures, but it's permanent operating. It's keep on operating like this. Here, ejection of vapor, the vapor is coming back, and so on and so on. Okay? So vapor is coming back, the mix, then as it is a porous media, it's coming naturally to the top by capillarity, then extracted again, so it's a permanent operating condition. And so you can, of course, try to use this part and this part also for other need. Okay, whereas the main objective is here to cool. The main thing is this. If you want, if you identify your cooling needs, it is here that you, and then you're designing all the other due to this need lab here. Okay. Okay. So for solar heating and cooling, one important thing, as I previously said, it is also the storage to maintain stability or to be able to answer to the need when you need it. And it is a problem. For cooling, it could be okay. For cooling, as I said previously, generally you need to cool when there is sun. So it's not a real problem. The main problem is to maintain stability of the process. And to maintain stability, you need to have a bit of thermal storage to have this bump effect if there is sun variation. For heating is delicate because usually you need heat when there is lack of sun. Okay. So here it's an illustration on a wool year. Okay. I show you some installation where you are coupling solar thermal for domestic hot water and heating system. Okay, floor heating system. This is this kind of house. Okay, in Chambéry, in my place, in winter for wool year. The system that is designed here is for heating and producing domestic hot water. Okay, so this is the months of January, February, March, April, May, December. So in December and January, it is here that it is the coldest months and the months where the number of hours per day is the weakest. Okay, so you can see in blue it is my solar thermal production. In red it is my needs. Okay, so you can directly feel that for solar thermal there is a phase change between what I can produce at the maximum, I don't need. I just need, why there is still a red bar? Because it's my domestic hot water. Okay, I just need domestic hot water. But the heating system is out. I don't need to heat my floor. And so I'm producing the maximum in July. Potential is July, but I just need that. Whereas I need a lot here in the winter time, but I can only produce that. Okay, so it is for that the thermal storage is essential, and it is could be essential between night and day, between one day to another, but at this scale could be also interseasonal, okay, to long-term thermal storage. And so it is the reason why thermochemical thermal storage is interesting, because as I told you, when you are injecting heat in your two media mix, you can keep them in two different tanks at ambient temperature. Okay, when you want to recover this heat, you just have to mix them. Whereas the other way to store, you are losing some energy, and so I found this very interesting to see problem of phase between your need and your capacity to produce. So there is three main ways to store energy. The first one is also developed for centuries and centuries. It is sensible heat. You are heating a body, okay, and when this body temperature is increasing of 1 degree, you know exactly the energy that you give it to him. It is density multiplied by the volume or the mass multiplied by the capacity heat, okay, multiplied by delta T. If you are increasing of 10 degree, you know the injection of heat that you have done. When this body is cooled down, okay, losing 1 degree, that means that he give MCP T, okay, delta T. So it's linear, it is sensible heat. The more efficient media is water, which has a very good capacity of storage, but of course limited by the temperature. If you are at 1000 degrees, you can't use water, okay? So sensible heat, that it is water, oil, concrete, could be a solid. You are heating a big block of concrete. The ground also, you can inject heat in the ground and extract it also. Then the second is latent heat, so phase change. Phase change material could be a solid or it could be a liquid, but very often it's around materials like paraffin, okay, a mix with paraffin and things like this. So you inject some heat, they are melting, and in order to melt, they need to absorb latent heat to make this possible. And when they are becoming solid again, they release this heat as latent heat. Okay, and the last one, it is sorption, as I just described. It is also used for a long-term thermal storage. The advantage between each technology is the density, okay? And it's interesting because if you increase the density of storage, that means that you decrease the volume of storage, okay? So if you want a long-term thermal storage, with sensible heat it will be enormous. If you use phase change material, you can divide the volume by 2, okay? If you use thermochemical, you can again divide it by 2 or more than 2, so at the end you reduce the volume. So the same amount of energy that you have stored, you can reduce the volume, okay? The problem is that the maturity. Sensible heat storage is very well known, very mastered, and no problem like this. Phase change, there are still some issue, especially in the aging of the materials, because there's also a limited number of cycles, like in a battery. Okay, you are melting, you are becoming solid, melting, solid, and these kind of materials are aging. And thermochemical, it's also to find the best material, but it's also to be able to master the reaction. If we imagine that my 2 stock of different media, if I want to take only a small shower, how should I combine them not to induce the wool reaction of my wool stock? I open my things, take the shower, and I will lose all my stock of energy. So it's more to how to give proportionally give back the thermal energy without generating the wool reaction. Okay, but And also the use for building application is to have safe materials. Okay, there's many possible materials, ammoniac, water, impossible to imagine to have it in your house. Okay, if there's a leak or if there's a if there's a leak, you can be attacked by ammoniac, and if there is a fire, it will imply a big disaster in your house. Okay, so there is also need to have safe materials for human application. So big families. So we will see several. To have an idea of density, so for sensible heat, so it's in French, but you can understand sensible heat in water, the density is around 60 kWh per cubic meter. You can double the density with a phase change material. The main issue is to be able to select the good phase change temperature. Okay. Because we'll show you that if you don't, phase change material is not a guarantee to have a best efficiency. If you made a mistake in the evaluation of the good phase change temperature, you can store less than with water. Okay, and then with thermochemical, the density could be between 200 and 500 kilowatt-hour per cubic meter. So it's very interesting to reduce the volume of storage if you want to increase the autonomy. Okay. So different way, different materials. So sensible heat, as I told you, is very simple. Mass, heat capacity multiplied by delta T. It's fully linear. So when you inject this energy, the body will increase of several degrees and so on. So we are using water, concrete, oil, and gravel and water for underground storage, or big time scale. Okay, so domestic, usually the surface of panel only for domestic is the more common, as not to be so important, so around 1 square meter per inhabitant. The more simple is this kind of collector. Okay, so with operating without electricity, with thermosiphon phenomena, as I previously showed to you. Usually you have the tank which is on the roof also. Here some image. We will never see that in a country where the winter are cold, okay? Because here the solar tank is outdoor, okay? And in a house it is a more deperditive component, okay? Because it is a place in a house where the temperature difference is more important. Inside your tank you can have 80 degrees. Outside your tank, if you are inside the house, you have 20 degrees, so you have 60 degrees of difference. If you put it outside in winter in a cold country, you have 80 degrees inside and you can have -10 outside. So 90 degrees of difference. So you imagine the weakness of insulation that you will have to put in order to avoid loss. Usually, it still remains the more deperditive component in a house because we don't put 30 centimeters of insulation around the tank. But it is a place in a house where you have the more big gradient of temperature between inside and outside, so most deperdition, it is a tank. So it is well adapted for country where during winter it's not so cool. Okay. We have more this with external flat plate collector and a thermal storage tank which is inside, in order to avoid to give too much calorie to the environment. The other advantage of this, it is the orientation. Okay, here it is horizontal. This is vertical, and it is the main parameter of efficiency of solar thermal storage, because in this configuration you have thermal stratification. Okay, when you are taking some hot water, the hot water is taking at the bottom, where the hot water is hotter. When you take hot water, you inject cold water for the grid. Okay, so what will happen? It is the cold water will progressively go at the top when you are using your solar tank. Okay, so there is a kind of piston effect. It's pushing slowly, 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 slowly. So in terms of capacity of human, you can use 90% of the thermal energy that you have stored. Because of this piston effect, there is no mix. Okay, here you can have 20 degree, 25, 30, until 80. Okay, so it's well stratified. That means that the cool water, when you are injected and you're extracting at the top, will progressively come without mixing, so that you can use 80% of the solar thermal energy that you have stored in your tank. Here, there is also thermal stratification, but only on this 8. Okay, it's the same. When you take solar hot water here at the top, you are injecting new cool water at the bottom, and here the mix is very fast. Okay, you have no piston effect, and as soon as you are injecting cool water, it will mix. So you are not using 90% of the thermal energy that you have stored. It's decreasing very fast. So if you want, for example, to compare, you can take a shower during 40 minutes here. Here, after 10 minutes, you will feel that it cool down. Okay? But it's not a problem in hot country, because in hot country, you prefer to have cool water when it's very hot than very hot water. Okay? So that's why it is developed in hot country and very efficient for this country. In France, there is a Réunion Island near Africa, where they are using that a lot. Okay, it's inexpensive, very efficient for local need. But this is very important, yes, thermal stratification, in order to have benefit of the whole capacity that has been stored, is very important. Okay? So this is a classical installation of solar thermal. You can also couple this to a heating system. And so you have a heat exchanger at the bottom that will heat, and you can have auxiliary. So when there is no sun, you have to inject heat to have domestic hot water. So usually in France it's electrical, okay, but in some country it could be with gas burner or things like this, so to complete. And you have a circulator and so on. So then to choose the temperature that you want at the end, you are combining this hot water with cool water to have the right temperature, expected temperature. One thing which is really important also, and it was my remark when I say in France, there was an audit about this kind of installation, and we find that there was a lot of problem. It is, for example, to be able to measure the temperature at the outlet of the solar thermal collector, and to see if the temperature is lower than the temperature in the tank to stop the circulation. And there was many installations where this kind of sensor were out of service. Okay, so that means that it was running even during the night. During the night, the solar thermal collector will be hot because it will take hot water from your tank, and so will emit a lot of radiation with the sky, the celeste volt. So that means that during the night you will empty your resource of energy which is in the tank, but you don't see nothing, because if the temperature is going down, auxiliary will take place of the solar collector. So there was a lot of energy consumption due to this system that was supposed to make some economy. And the classical people living in the house will not check if they are consuming electricity or solar thermal. They have hot water. They are thinking that they use hot water coming from the sun. Mainly, if this is not working, it's mainly coming from the auxiliary. Okay? So it has to be very, very important to check that everything is working in order to have not the reverse. Finally, it's the opposite. You are consuming more energy because you are extracting energy and to give it outside. Very important. Sorry. Okay. If you want to optimize with thermal stratification, depending of the outlet temperature of the solar thermal collector, there is some sophisticated tank that allow to inject the water at different level in the balloon, in the tank. Okay. So there is a measure of the temperature around the height, and if you are going out at 50 degrees, it will inject the water at the level where it's around 50 degrees in order not to perturbate to all the stratification.
And then a lot of controls.
Yes.
A lot of control in it and thermocouples.
Yeah, yes.
Sensors.
It's important, just because you can have yes, a loss of efficiency.
Of these tubes are from the collectors.
So they are coming from the collectors, yes. Okay, so another way to have sensitive short-term storage, it was some houses that were developed in the 80s, but at that time, unfortunately, the insulation of this house was not good. So this system was finally not so developed, but it is to use kind of greenhouse, to generate hot air and to inject underground on stones. Okay, so and during the night to make the ventilation going underground to take the heat that has been stored on the stones to heat the house. After there was some development with phase change materials, with sphere of phase change materials. We are injecting it underground and then recover. I like also this system that now is started again to be investigated, because now the houses are more insulated. So it's interesting. But when it was firstly designed, there was too much loss and finally weak bring of this system compared to the energy consumption. It was very important because air. So it's an example. So now I'm also giving as a lecture to my student. It's a kind of porous media, okay, and you are recovering a part of it during the day. So we compute in order to have an evaluation of the temperature of this bed of stones, okay, and capacity of storage. So interesting. When we are going at the bigger scale, because sensible heat, it could be at the scale of a house, okay, domestic hot water, heating, but of course at the time to seasonal storage. As I told you, usually we are producing a lot during summer and we need a lot during winter. So at the bigger scale, it is underground, could be a swimming pool, like a swimming pool, a big water balloon, but generally it is a mix with a gravel plus water, okay? Or more and more fun is to have some pillars so that inject some heat in the ground. Of course, the ground is not very well insulated, so you are losing some heat, but you can store a lot heating the ground and then extract this during winter time when you need. Okay. Example. So it's a real in Germany here. You can see it's after they will build a new building at the top. It is all underground of the length of the building. Okay, it's a kind of swimming pool. You can see the scale. Here you have an engine. Here you have a man. Okay, so just to give you an idea of the scale, it's a big tank where there's a mix between gravel and water. Usually. So typically this is for inter-season storage. You are injecting a lot of heat during summertime and take it during winter. Okay? So you can imagine in terms of maintenance that you have also to check that the civil structure is okay, and so on and so on. So example here is a 12,000 cubic meter of storage, and the same here. Or you have now this kind of systems that are more and more developed, less expensive, is to make some borehole and to inject the heat by the circulation of water inside the borehole in the ground. Okay, borehole that could have 40, 50 meters depth, and many boreholes. So at the scale of a district, each building that are generating heat during summertime are injecting underground, and then it is the reverse circulation for winter. Okay. Example here, it's in Zurich. It is hybrid also photovoltaic thermal collector that are used for both electricity generation and injection of heat in the ground. And so there's a mix between electrical, thermal. Now, regarding latent heat, as I told you, the temperature here, the energy which is stored. So it is linear when it is sensible heat. When it is not sensible, when it is latent, you start to heat, to inject energy, okay, at a certain temperature, phase change temperature. You have a big shift, a big gap, which is related to the latent heat of the phase change, okay? And then, when, for example, it is fully liquid, it behaves again like sensible heat storage. Sensible heat storage when it is solid, when it reaches the phase change temperature, it melts, big storage of heat due to latent heat, and then it behaves as a liquid that you continue to heat, so like a sensible heat storage. Okay, so it is here that it is interesting. Okay. So all the family. Some example here that we can take this afternoon if we can reach the storage design. So usually you have you can have two heat mass capacity when it is solid or when it is liquid. So 1 and 2, and also the example of latent heat. So for the sensible heat, it is MCP delta T. For the latent energy, it is latent energy multiplied by the mass only. It is at 1 temperature. So this is by kilojoule per kilogram. And then again, when it is liquid, it is MCP delta T to have an evaluation of the energy that you are storing. Okay. And so you have also for higher temperature here. Of course, it is for concentration, solar thermal concentration application. When you reach 800 degrees, you can't use any more paraffin, water, and so on. It is some specific materials, usually more or less dangerous for the environment. So we will not find that directly in a house or in a district scale. It is dedicated to solar power concentration. Okay. It's okay? Question? Okay, so this regarding phase change material now, there is try to find new kind of non-paraffin compounds, because in the paraffin there is at the backside petrol. Okay, so now try to find more eco biosourced materials like fat of animals, for example. It's exchange materials. They try to investigate many different new, better eco-friendly materials. Okay. So this is the main family. Yeah, here fatty acid to try to investigate. Yes, more. Okay, so it's a main characteristic. When you are with salt, so it could be dangerous for environment. It could be also very corrosive. So it's important to check the volume of storage for the big power station, solar power station, where there is big tank of this kind of salt. Okay, so there's a lot of range, of course, of temperature, low temperature, which is more for application in building, medium temperature, and high temperature, which is dedicated to solar thermal concentration. You can have mix between sensible and phase change. For example, you can, in your domestic hot water tank, reduce the scale of the tank by mixing water with this kind of nodules. Okay, so this is a sphere which is filled with phase change material. You could put that in your solar tank. It will allow to reduce your tank. Okay, we'll see that this afternoon. And so it can evolve. One thing to be cautioned when you put phase change material in a finite volume, it is that the volume is changing between liquid and solid. Okay, and there was a lot of problem in the first experience that it was fully filled and exploded. Okay, so it's never fully filled in order to allow to have difference of volume between liquid and solid. Very important. There was a lot of experiment put on the brick and so on. The brick were exploding, due to the phase change difference of volume. So my remark regarding the important thing is to design, to identify the temperature of changing the phase. Okay, here if I compare so energy which is stored with temperature, I take some water in red. Okay, I start to bring it to this water tank, and it is linear depending of the temperature. This is at 85 degrees the energy that I have stored. If I have a phase change material, usually the heat mass of the phase change material is not as good as the water. Okay, is lower. Water is a very good materials with the density and the heat mass is very good. So you are starting lower, okay, but you are heating your solid, okay. Then at a certain point, you store more due to phase change, and then you continue. But imagine that you are operating here, okay, around 95 degrees. Finally, you store less energy with your phase change material than with your water, okay? Because we didn't identify the more appropriate phase change temperature for my application. So an important remark is that it's not because you are changing from sensible to phase change material that you will be more efficient. It has to be very caution on the choice of the temperature. And it is the main issue generally in the application. So people are speaking a lot of phase change material is beautiful and so on and so on. Not so, it's not an obligation. You can be less efficient. So it has to keep that in mind each time. If it was sensible heat, will it be more or less efficient? And for this, it's okay. If I'm operating here, I'm storing more energy than water, okay? But if I'm operating here, it's less efficient. So there was some attempt to put that on a very light wall in order to increase the inertia, the thermal mass of lighthouse, okay? Because existing buildings, in some part they are not inert and can store or can dump the heat effect out from outside. So there was some attempt to put some in some light wall, but it's very important to design the temperature. At which temperature we will put phase change material here? Is it 30 degrees in order to be able to absorb a part of it during a hot time? Is it 25? Is it 35? So there was two kind of materials that have been developed by chemical industry, Dupont de Nemours and BASF have developed some materials for construction like this, with two different temperatures. So it's interesting. There was a thing like this also, as I told you, in brick. Okay, it was in such configuration. If you don't allow the kind of expansion, the brick will be fully destroyed. So I will, and another issue now is, so we speak a lot about heat storage, but the issue also will be to store the cool, okay, so at low temperature. So now there is also some study on at low temperature to be able to cool down materials that is able to phase change at also low temperature to keep the cool. Okay, so it's interesting also kind of materials to store when you are generating cool to keep this and to store it. Okay, so you can see the melting temperature that could be interesting to investigate. Okay, so at a bigger scale, so I speak about small scale phase change material storage for my domestic hot water. Bigger scale application is for concentration. We have seen that, but we didn't focus on the storage. Here it is a 2 tank that are for this Andasol, which is 50 megawatt, that allow to have an autonomy of 7 hours. Okay, typically it is during the night. Okay, because it is in the desert, so it's very rare that there is some clouds. Even if there are some clouds, it will not be during 7 hours. Is to have operating configuration night and day, so it's 7 hours. So we can have an idea. It could have to store 6,200 tons of phase change material, which is molten nitrate salt. Okay, so in this kind of tank, this is very corrosive, and this is very dangerous if there is a leak. Okay, that explains that it is classified, even if it looks like green power generation, it is classified as dangerous. Okay, so usually there is fireman not far. Okay, in order if there is a problem. It is Seveso classification. Okay, to give you a rough idea of the size of such volume for phase change materials. Question? Okay, so we have seen that. For absorption, so there is several couple, lithium bromide, ammonia, O, so on. So the criteria is regeneration by heat, okay, and easy to handle, to couple, low investment cost, of course. Aging of the materials has to be taken in consideration. This is a classical way to store. Okay, we have already seen that for cooling system. It is the same. Okay, the same element. It's like an absorption machine. And so the coupling with the solar. So it's the same as the absorption machine, but it's not working continuously. When we separate the two media, we store them until we want again to have the heat. Okay, it's not a cycle where we are heating and cooling and so on. See, when we are heating during summertime, for example, we are generating two big volumes of the two media, and during winter time, when we want this heat back, we put them together again. Okay. There is no so it's summer operating condition, okay, and it is winter operating condition when you want to have your heat back. There is no real application for building at this scale long term. There was some prototyping in my institute at Ines. There is one full-scale prototyping for a domestic house. Okay, try to have fully autonomy in heat for the whole year. Okay, so to give you an idea, I have not the picture, but to give you an idea, you have a house and you have a garage for your car. So the volume which is necessary to be fully autonomous in terms of heating needs, it is to fill the garage with the thermochemical materials. Okay, so it stay a big volume, even if it is thermochemical, it stay a big volume of storage. Okay. So you have the house and the garage, and you forget your garage, and you put the thermochemical storage here. But you are fully autonomous. Okay. Of course, they have to have some improvement, and for sure it will gain in terms of volume reduction, things like this. Okay, so this is like a adsorption or absorption machine, but it is intermittent. You are operating in one direction during one period, and you are operating in the other direction during the other period. It's not a cycling like a machine for cooling. Okay? So what is important? It is operating temperature, energy density, but it is the case for all means of storage. For battery, it's also the case. The energy density of the battery, we have seen in our PV project that there was different battery with different energy density. That was in kilowatt hour per kilogram of battery. It's the same here. It's what kilogram hour I can store per cubic meter. Optimization of time of management, of course, it's a huge issue, and integration of storage in the building. That means that a lot of things are possible, but not in the building, because you are living in the building, and it is necessary to have safe system. Okay, safe system. If there is a leak, it has not to be dangerous for you. And if there is a fire, it has also not to be to enhance the fire effect. Okay, so it is it's a big limitation for building application, because there is many different couples that are very efficient in terms of absorption, but never seen in building because of these two parameters: sanitary reason and safety reason when there is fire. Okay. So the advantage, there is a lot also, not only some constraints, but you can really highlight the use of solar thermal thanks to this system. Image about storing of cool. Here it's micro capsule of phase change material. We call that ice coolie. Okay, so that you can also transport the cool on distance. So it is investigate not only to be able to transport it in the urban grid, but also to transport it, to transport cool, because the cooling needs are more and more big. Some example, you can put that also on the slabs, on the floor, on the structure. So this is for cooling. Eh? Okay, I've already said that. A short thing, I don't know what time is it. A short thing regarding grid. Storage is essential. So in the coupling with the grid, in order to optimize the flexibility. Storage could be for thermal energy, could be for electrical energy. Electrical energy, we try to couple the storage with electrical vehicle, to use electrical vehicle to store the electrical energy. But it is, yes, a key element in the management of energy at the scale of territory. As I remind you, you are producing, but you have also to transform, to distribute and to store in order to be well adapted to the energy need. Because you are producing very often when you don't need, and you need when you can't produce. Okay, so even if you are connected to the grid, now more and more often, the storage is becoming even for electricity. Okay, because of the price of electricity, which can fluctuate a lot. So it could be interesting to look at the storage of electricity on your car or on battery, to use it when the price is low, and to use this capacity that you have stored when the price of the grid is high. It's the same for thermal. Okay? You can mix with different energy vectors. It could be heat, it could be electricity, it could be hydrogen. And now in my lab, some are playing with all these kind of vector to transfer to one vector to another, depending on the energy management and flexibility that you need. Don't forget that each transformation is inducing a loss also, so it's good to play, but you can lose a lot. So this is an illustration. There is many ways to store, to convert energy in mechanical, in thermal, low temperature, thermal, high temperature, in chemical, okay, in biological, and so on and so on. So there are many things in order to answer to the final use, even if you are coupled to the grid. This is in English, sorry. It's better. So for this you have to know about the grid, okay? And to enhance the power and quality and reliability, you have to trust in some sensors, some data, some huge need of control, because to control this complexity, to be able to anticipate. So that's the main issue that you have to take in consideration. This is the whole complexity of a grid that you have to deal with. I will not spend too much time on this, but more and more you need to have some data about the needs, about the condition of your system, about the condition of the grids, about the climate also, because the climate will change, could make the needs evolve. And so in our part, we are more working in the evaluation of the needs and the potential of solar at the scale of a territory, while considering the climate change, so kind of prediction of the meteo. Okay. Maybe I have not much time, but I will leave you read that. I wanted just to show you so that we are doing at the scale of a city. We are working in two things: to be able to predict the solar potential at the scale of the territory, and to predict also the building need at the scale of the territory, due to prediction of both, so radiation, of course, but also meteo, urban climate. Okay. So we are using different tools like Solène microclimat in order to evaluate local climate, Rhino grasshopper, different tools. At that time, we are using some tools that are coupled to meteorological tools, okay, so big scale, like weather research forecast. I will show you some results. And we are modelizing, taking in consideration the difference of energy budget that we have at the scale of a city compared to countryside. If we look at the energy budget of the city compared to countryside, this is what I receive from the sun, okay? It is the same for urban and countryside. In terms, we see that there is a certain part which is reflected, because there is lake, there is trees, okay? This part is much more smaller at the same as the city, because the city is more absorbing, okay? In terms of incoming infrared is the same. Okay. Then outgoing infrared. Outgoing infrared, so it is what is emitted in infrared, is 8.5 here. It is 10.3 here. That means that it emits more at the city scale than in countryside. Why?
You have a lot of carbon dioxide, greenhouse gases.
No. It is emission. No.
Lot of reflections.
No reflection. Yes, reflection is here. There's more reflection on the countryside than here. But here it is emission infrared. It is infrared emission is directly linked to the temperature of the surface. Emission of body is sigma temperature power 4. So here outgoing infrared is bigger because the surface temperature is bigger. Okay, so it's a good point, but it's not a good point because in reality, yes, temperature is bigger. Latent heat here is 1 point, is a double here. So it is related to what? It is related to the activity of the forest. The trees are evaporate, okay, evapotranspiration, and also because there's water, lake, and so there evaporation. Latent heat is so the double here, whereas here there is less tree and no lake, except in the campus here. But very often there is no lake in the city. So you are evacuate more here by latent heat than here. Regarding storage, is 0.3 here, it's 1.3 here, because majority of the materials in the city are storing energy. It's sensible heat, concrete, road, it's heavy materials, it's good, sensible heat storage materials. So we are storing more. And sensible heat, what is related? See, it's a bit more in cities than here. What could be this sensible heat extraction? It's related to the wind. When there is wind, if you look at this far away, it looks like an heat exchanger. So when the wind is crossing, there is kind of induced phenomenon. So you have more convective heat exchange. So sensible heat is a bit higher here than here. And you have this green arrow, which is an injection of heat. And it is anthropogenic heat. It is related to human activity. Classical cooling system. Okay, these are rejection outside heat. You are taking inside heat, but you are rejecting outside heat. So if we generalize that, it will induce the rejection of heat here. You have also car, circulation, traffic jam, industry, and so on that are releasing heat. Car, an engine efficiency is 30%. 30% is used in mechanical to move. 70% is rejected as heat. So this is a key issue also, that you have bad balance in terms of energy, thermal energy, due to absorbing. Most of the surface are absorbing, they are dark, the roads are dark, the roof are dark, and you are absorbing, you are storing, because it's heavy materials, and you are injecting more heat due to activity, so cooling system, traffic jam, and so on and so on. So this made it's necessary to modelize that in order to have an idea of the temperature in the city, in order to have an idea of the needs in terms of energy. It will impact the energy needs of building. Okay? And to find solution to try to cool down, to mitigate this without injecting heat. So the main issue is that we will develop more and more the classical cooling systems that are efficient, but that are rejecting it. The more we will need to cool, the more we will induce a necessity to cool. It's very important to be aware of that. So it is in this way that solar thermal cooling systems are interesting now, because they are not rejecting heat like this. And centralized production of cool also, it's also an issue. Okay, I can speak for a long time about that. It's about urban planning, but I want to show you the last results I have with a PhD working in modeling of local climate on the base of the modeling of big-scale meteorological. So he's using the tools weather research forecasting model, WRF, and try to model at the scale of a territory and then go down at the scale of a city to evaluate this. This, for example, for the city of Lyon. So here it's a part of France, Switzerland is here, my institute is here, and Lyon is here. So he's working, you see the scale on which he is working, multi-scale. So it is the quarter southwest of France, and then going down to investigate at the scale. So it's a very computation consuming. And there is identification regarding the different districts of Lyon, possible different local thermal zone, okay, due to morphology, due to the size of building, the color of the building, the composition. So there are 10 different climates have been identified due to the morphology of the city. And so now is kind of clustering of this, all of these 10 climates can be seen. So it's analyzing the shape, the morphology of the district. And then to give some data like this, where you can have the temperature, the radiation, depending of the different districts. But it's not so nice at this scale because you don't see really things, but it's to classify the different zones of the city in order of local climate, and then after to be able to make the link. We are interested to see the climate and to see if we put some PV panels in this climate, what it will change in terms of local climate. Will it be worse or will be better? There is still a controversy about that. So he's testing different surface emissivity and surface composition to look at the impact on this. And so at the end, he is able to, in a different place, to give the temperature, local temperature, depending of the morphology he has chosen and the building envelope characteristic, and especially PV. Okay, so I can maybe conclude on it, but I will leave you all the information if you are interested by the other topic, which is able to identify the real building needs, taking in consideration a more realistic climate, and then to make the link with the way to answer to the building needs thanks to solar energy. Okay, thank you. So this afternoon we will have the tutorials about desiccant cooling. Okay, so take the paper sheet with the diagram, the principle of the desiccant cooling components. That has been sent, I think, to the people online, and we'll see more deeply, but roughly the main principle of this system and the main consumption in terms of electricity and water compared to a classical one. Okay? And if we have time, design the thermal storage in order to be able to maintain stability for 3 hours if there is no sun. Okay? Thank you and see you soon.
So it's a very nice presentation. We have learned many things today. So like cooling and heating by using solar, and also at different temperatures how we can use it. So it's really very interesting. So and the very interesting thing what we received an email. This new scheme with India and France has opened for internship and all. It's a very good news. Just now I received an email. Thank you. But what I request you everyone, please be here before time. 3 o'clock we are going to start, but please be here by 2:55 or 50. Okay. Thank you.
Thank you.
And also there is an announcement today evening. We have arranged one dinner in our department, and maybe before we start for dinner, there will be one movie screening. Okay, that's we are planning what movie we are going to screen, and not exactly movie, it's a documentary kind. Okay, then we will have dinner. Right. Okay.